Okay, let's try this one more time with rectangles. Let's look at another scenario here. So we are looking at JKLM and how it maps to PQRS. So point J maps to point P, and we're looking at these so we can tell whether we made a rotation, a reflection, or a translation. K maps to Q. L maps to R. And let's see, let's use purple. And M maps to S. So we're starting with JKLM. So this time we're starting with our small square, and we are going to use a sequence of rigid motion followed by a dilation to produce similar square PQRS. So as I'm looking at these points, I see that this is not a translation. I didn't take my little square and slide it down because point J was on the top left and now it's in the bottom left. Also, that first might make me think that this is a rotation, like maybe I rotated this 90 degrees and moved it from quadrant 2 down to quadrant 3. But then if I look at another point, then if that's the case, then M should map here, and that doesn't match up. So this is not a translation and not a rotation, but it does look like a reflection. So halfway in between this square and this square, I'm going to draw my line of reflection. So this must be the line that I'm reflecting across. And this line is called y equals 1 because it is 1 unit above the x-axis. So it's constantly at a y value of positive 1. So now what I'm going to do, let's go ahead and reflect this square down, and then we can look at how to dilate it. So if point K is 1 unit away from the line of reflection, if it's 1 above, then it's going to reflect to 1 below. So that's going to be, why is this not going blue? There we go. So that's going to be K prime right there. And then as I look at point J, J is 1, 2, 3 units above the line of reflection, so it needs to move 1, 2, 3 units below the line of reflection. So this is going to become J prime. M prime is 3 units above the line of reflection, so it's going to move, M prime is going to move down here. And L is 1 unit above, so its reflection will be 1 unit below. So now we have this square. Oh, my lines are not very straight. Oh boy. Hopefully you get the idea. Now I need to look at how to dilate this. So if I know that my center of dilation is 0, 0, let's draw some lines from the origin, which is right here. So let's go ahead and draw some lines through each of my points. Oh, oops. Sorry, I didn't want that. Okay, I want to make an actual line. There we go. Okay, let's try this again. So from the origin, I'm going to make a line down through point S. So when I dilate, it looks like this is already on the path where M prime will map to S. Okay, now let's draw from the origin a ray through point P here, and it looks like J prime will map to P. And as I draw my ray through here, K prime will map to Q, and L can stay where it is. So I don't have to translate, or I don't have to make any other changes. So all that I had to do was reflect across the line, y equals 1, and then I do dilate, so now I need to figure out what my scale factor is. So to do that, let's look at our points. So I'm going to have to erase some of this to I don't want to erase that. Oh, this is not working very well. Sorry. I just want to clean it up a little bit so that we can see better. So let's maybe just drag some of this out of the way. So that we can see. All right, well, that didn't work well. There we go. Okay, because I need to look at my points that are going to map to each other. So L prime is going to map to R here. So the coordinates of L prime are -1, 0, and that's going to map to the points R, which is at -3, 0. And then K prime is right here at -3, 0. And that's going to map to Q, which is at -9, 0. And then I have J prime, which is at -3, -2. And J prime is going to map to point P, which is at -9, -6. And M prime is at -2, -2. And that's going to map to point S, which is -3, -6. So what I'm looking at is trying to find my scale factor. So my scale factor is going to be the number that I multiply by that's going to make this small square into a bigger one. So since I'm creating an enlargement, I need a number that's bigger than 1. So I'm thinking, okay, how do I turn a -1 into a -3? Well, if I multiply by 3, -1 times 3 is -3. Does that work here? -3 times 3 is -9. -3 times 3 is -9. -2 times 3 is -6. -2 times 3. Oops, we didn't get this one right. Let's see. Oh, we didn't write this point correctly. This should have been -1, -2. So a -1 times 3 does give us -3, and -2 times 3 gives us -6. So our scale factor is a 3 in this case because all of my points are 3 times as far away from the origin. So those were the two transformations we had to make. We had to reflect this square across the line y equals 1 and then dilate it using a scale factor of 3. Okay, and finally, the last thing we're going to look at is in part 3, we're going to look at the effects of dilation on angles and the effects on line segments. So what we find is that all angles, slide this up, all angles are taken to angles of the same measure. So my angles are always going to be congruent. Notice angle A is going to be congruent to angle A. In this triangle, angle B is going to be congruent to angle D, and angle C is going to be congruent to angle E. So my corresponding angles are going to be equal to each other. A is equal to A, B is equal to D, and C is equal to E. The effect on line segments, however, is different. Corresponding sides in similar figures are going to be proportional, or they're going to have a common ratio. So this ratio is going to be equal to the scale factor. So in our last problem, if we had a scale factor of 3, then all of my sides in this bigger square should be 3 times as big as the sides in my smaller squares, so a 3-to-1 ratio. So the last part we need to know how to do is, as we're looking to see, is triangle MNO similar to triangle PQO? I can check and make sure that my corresponding sides are equal in length, and that's how I can prove that they're similar. So let's look first at side MN. I'm looking at the first 2 letters in my triangle, so I need to compare it to the corresponding side, which will be PQ. So MN is 2 units and PQ is 3 units. Okay, so right now we have a 2-to-3 ratio. Let's see if that works for the other side lengths. Okay, as I look at NO, now I'm comparing the last 2 letters, so I'm going to compare the last 2 here. So I'm going to look at QO. NO is 1, 2, 3, 4 units long, and QO is 6 units long, right? So this is a 4-to-6 ratio, which would reduce to 2-to-3. So let's check our last set of sides, and that's going to be MO, and I'm going to compare MO to PO. Okay, now these are on the diagonal, so I can't really compare the distance of these in the same way I can as the horizontal and vertical sides. But if we have 2 sides that are in proportion, then the third sides will have to be as well. So we could say yes, these triangles are similar because corresponding sides are proportionate. And they have a scale factor of 2-to-3, or 2/3. And finally, as we look at this, which 2 triangles are similar? So there's one triangle that I can rule out right off the bat, because to be similar, I have to have equal angle measures and proportionate side lengths. And I see one triangle that definitely is not like the others, and that's this one. This one's not a right triangle, and these other 3 are. So this definitely cannot be similar to these because the angles are not the same. However, these 3 each have a right angle, so now let me check corresponding sides. So I need to compare side AB to side FG. And this is 2, this is 4, and this is 2. So far, both of these smaller triangles are in a 2-to-4 proportion with this larger triangle ABC. Now let's compare the other leg that makes up the right angle. So we have 1, 2, 3, 4 units here. So this is 4 again. And I need to compare that to this, which is 2, and to this, which is 4. So I know that this triangle is no longer in proportion to this one because both of these side lengths are the same and these are not. So I'm going to cross this one out. But since these 2 triangles have 2 sets of corresponding sides, their third side, by definition, must also be proportional. So we could say that triangle ABC is similar to triangle and this one we're going to name corresponding sides. So sorry, I was just checking. If I take this triangle and I flip it up, I reflect it over this line, then the corresponding sides would be G, F, E. So A corresponds to G, B corresponds to F, and C corresponds to E.